Chapter 9, Section 9, Part 2. What good is a power series expansion? In our previous lesson, we considered the derivative and antiderivative of the power series for function f with a radius of convergence r. We concluded d of x, the derivative of the power series of f, is the derivative of f with radius of convergence r. We also concluded that a of x, the antiderivative of the power series of f, is the antiderivative of f with radius of convergence r. Having practiced finding d of x and a of x, the functions in the previous lesson, we want to apply this knowledge. So what good is a power series expansion? One application of power series expansion is the approximation of difficult-to-compute integrals. Many commonly utilized functions have established power series representations. The sine of x has a power series that's equal to the sum from k equaling 0 to infinity of negative 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. Taking the derivative of this three-part equation and simplifying, we obtain that cosine of x is equal to the sum from k equaling 0 to infinity of negative 1 to the k x to the 2k over 2k factorial. By the theorem we learned about in the previous lesson, cosine of x and its power series are truly the derivative of sine of x and its power series. Now let's consider an example. For the integral from 0 to 1 sine of x squared dx, we would like to evaluate the integral with an error of less than 10 to the negative sixth. But neither u substitution nor integration by parts gets us an antiderivative that we can use for this problem. But if we could try rewriting the expression as a power series, we might have greater success. Since power series expansion for sine of x is sine of x equaling the sum from k equaling 0 to infinity of negative 1 to the k x to the 2k plus 1 over 2k plus 1 factorial, we can obtain the power series for sine of x squared by replacing all the x's with an x squared. So the power series expansion for sine of x squared is the sum from k equaling 0 to infinity of negative 1 to the k, but now x to the 4k plus 2 over 2k plus 1 factorial. Replacing sine of x squared with the summation and showing the first four terms, we can now do an antiderivative. So the integral from 0 to 1 of sine of x squared dx is approximately equal to x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial from 0 to 1. Substituting in and simplifying, we obtain that the approximate value is 0.310268158. But how good is this approximation? Does it meet the requirement of being an error of less than 10 to the negative sixth? Well, since this approximation comes from an alternating series, our approximation differs from the actual value by no more than the absolute value of the next term in the alternating series. Since we know 4 terms, the next term would be the 1 over 19 times 9 factorial term, which is approximately 1.45 times 10 to the negative 7th. So, indeed, we have found our integral with an error of less than 10 to the negative 6th.